250 million years ago, Earth became a world of desert, scorching heat, and deadly silence. It was the Permian, the time of the greatest extinction in our planet's history. How did life collapse, and what clues remain today? Stay with us as we uncover this story. If you enjoy it, please like, subscribe, and share, and tell us in the comments which ancient world would you want to witness if you could. Thank you for watching. Now let's begin. The Permian begins with the land of Earth drawn together into one great supercontinent. This landmass is called Pangaea, and it forms through long, slow movements of the crust. Earlier fragments of continental plates that drifted apart and collided in older eras now stand locked in place, forming a single continuous body of land that stretches nearly from pole to pole. When geologists describe Pangaea, they mean a union of almost all land that exists at the time, from the northern regions of what will one day become North America, Europe, and Asia, to the southern reaches that include South America, Africa, India, Antarctica, and Australia. The margins of the supercontinent press against one another along long mountain belts, created by the collisions that closed ancient oceans. These belts include the range known as the Ural Mountains, which rise where Europe and Siberia meet, and the Appalachians, which stretch across eastern North America, once towering far higher than their modern remains. These mountain chains are reminders of the power of continental convergence. The unification of land into Pangaea changes every part of Earth's system. The arrangement of continents plays a controlling role in climate-ocean currents and ecosystems. A single landmass with immense breadth has different properties than scattered continents surrounded by sea. The central parts of Pangaea are far from any ocean, which means they are isolated from sources of moisture. Winds that carry water vapor lose it long before reaching the interior, so the heart of Pangaea becomes dry. This dryness is not temporary but persistent, lasting for tens of millions of years. In these central regions, moisture-loving forests cannot survive and open deserts expand. The outline of Pangaea is not a neat circle, but an irregular shape that resembles a giant letter C. The eastern side of the land curves inward, forming a gulf called the Tethys Ocean. This sea lies between the northern arm of the continent known as Laurasia and the southern arm called Gondwana. The Tethys is shallow in many areas, with broad continental shelves where reefs grow and marine life thrives. In contrast, the outer edges of Pangaea are bordered by long and relatively straight coastlines that face the wide expanse of the global Panthalassa Ocean. The Panthalassa is vast, covering nearly all of Earth's surface that is not occupied by Pangaea, stretching unbroken around the globe. The coastlines of Pangaea that meet the Panthalassa are often steep and exposed, with few indentations to break the power of ocean currents and waves. The vast scale of Pangaea creates a strong contrast between conditions at its edges and at its centre. Along the coasts, climates are moderated by the sea, and rainfall can occur where winds bring moisture inland. But as one moves into the continental interior, the environment grows more extreme. Summers become hotter, and winters colder, with little rainfall in between. These conditions are called continentality, meaning that the climate is shaped by the presence of a large continent, rather than the moderating influence of an ocean. The interior of Pangaea develops immense dune fields, dry basins and salt flats, while the coasts hold more varied environments with rivers, wetlands, and fertile plains. The formation of Pangaea also changes the flow of the atmosphere. Wind patterns are guided by the placement of land and sea. With so much land joined together, winds travel differently than they did when continents were separate. Large seasonal shifts occur, creating strong monsoons in some regions, especially near the Tethys Ocean. A monsoon is a seasonal reversal of winds that brings heavy rains at one time of year and dry air at another. In the Permian, these monsoons affect the eastern and southern parts of the supercontinent, but they do not reach far inland. The central deserts remain parched, while coastal and near-coastal areas may receive alternating wet and dry seasons. Geologists know the shape of Pangaea and the environments it hosts through multiple lines of evidence. Rocks preserve the sediments of deserts, rivers, and shallow seas. Mountain belts show where continents collided. Paleomagnetic signals preserved in rocks record the latitudes where they formed, helping reconstruct their ancient positions. Fossils of plants and animals reveal which land masses were joined, since identical species occur across what are now widely separated continents. In the southern parts of Pangaea, for example, the distinctive leaf impressions of the Glossopteris plant appear in rocks of the same age across Africa, India, South America, and Antarctica. This broad distribution is only possible if these lands were once connected. The unity of Pangaea also affects ocean circulation. With only one great ocean, Panthalassa, the patterns of water movement differ from those in times with several smaller oceans. Currents circle around the globe without obstruction, and deep waters form in high latitudes, but some parts of the ocean remain stagnant where circulation does not reach. This uneven mixing will later play a role in conditions that stress marine life. At the same time, shallow seas along the edges of Pangaea provide broad habitats where carbonate platforms and reefs can grow. Thus, the same arrangement of land and sea creates both thriving environments and severe deserts, both fertile shelves and dry continental basins. The Permian world is therefore one of contrasts, all shaped by the geometry of Pangaea. There are humid coastal regions where rivers flow and wetlands gather, but these areas are narrow compared to the vast dry lands inland. There are mountain chains where tectonic collisions have raised high peaks, and there are low basins where sediments accumulate layer upon layer. There are tropical belts with strong monsoons, and there are temperate zones with strong seasonal swings. Life must adapt to each of these settings, and the physical environment places strict limits on what kinds of plants and animals can thrive. As the Permian progresses, these contrasts remain a defining feature of the period. The deserts of Pangaea are not brief episodes but lasting landscapes. The mountain belts do not vanish quickly, but endure as prominent topographic highs. The shallow seas along the Tethys remain centres of biodiversity for much of the time, while the interiors grow ever more arid. The supercontinent continues to shape the climate, the hydrology, and the biosphere through its immense size and unified form. The Earth in the Permian is therefore a world dominated by land more than sea, by continental influence more than oceanic moderation, and by the consequences of one great supercontinent joined together. The interior of Pangaea is shaped not only by its distance from the sea, but also by the great scale of its land surfaces, which creates climates that are severe, dry, and difficult for life to endure. When moist winds rise from the ocean and travel across the margins of the supercontinent, the air gradually loses water as rainfall. By the time these winds reach the central plains, little moisture remains. This process leaves most of the interior under constant aridity. The farther inland one moves, the more rainfall decreases and the more evident the dry conditions become. Rivers that flow into these central areas are often seasonal, swelling during rare storms, but quickly shrinking into dry channels once the rains pass. Floodplains fill with sediments during these brief floods, and then lie exposed for long periods under the sun. The result is a land of extremes where bursts of water contrast with years of near absence. The soils of the interior regions reflect these conditions. Red beds, which are deposits rich in iron oxides, are common across Permian basins. Their colour forms when iron minerals are exposed to oxygen in the atmosphere under dry and oxidizing conditions. These rocks indicate that much of the Permian interior is not humid and forested, but instead arid and open with soils subject to long exposure and little leaching. Loess deposits, which are fine silt, carried by winds also accumulate, showing that strong dry winds move across exposed surfaces and carry dust over great distances. In some areas, this dust settles into thick blankets of sediment, forming loess plains that stretch for hundreds of kilometers. The combination of red beds and loess illustrates how dry climates dominate, leaving behind clear geological signals. Seasonal changes intensify the challenges of living in the interior. Summers are extremely hot as the land absorbs and retains heat, while winters are cold because there is no nearby ocean to moderate temperature swings. These extremes are evidence of strong continentality. Without the stabilizing influence of water which warms and cools slowly, the land responds quickly to changes in solar energy. This means that regions in the middle of Pangaea experience searing summers and harsh winters with few moderate seasons. The shifts between these extremes are rapid, stressing both ecosystems and landscapes. The cycle of drying and flooding leaves inland basins filled with evaporites. Evaporites are minerals such as halite and gypsum that precipitate when bodies of water evaporate. In the Permian, shallow lakes and seas often form in restricted basins, where inflow of water is limited and evaporation is strong. Over time, as the water evaporates, salts crystallize and settle, creating thick deposits. These evaporite layers are widespread in Permian rocks and form some of the thickest and most extensive salt deposits in Earth's history. They show that evaporation was a powerful force stripping away water and leaving behind only the solid remains of dissolved minerals. Along with salts, dunes become characteristic of the Permian interior. Vast erg systems, which are seas of sand, cover thousands of square kilometers. Wind shapes the sand into dunes that can reach heights of over 100 meters. These dunes migrate slowly as the wind pushes grains upward on one side and lets them slide down on the other. Cross-bedding, a feature visible in the rock record, is created by this process, preserving the angled layers of ancient dune faces. Geologists study these structures to recognize fossilized desert environments. The existence of such enormous dune fields across Permian formations demonstrates that wind and dryness dominate the central landmass for long stretches of time. The vegetation of the interior must adjust to these challenging conditions. Seed ferns and conifers, especially species with drought-resistant features, become the dominant plants. They are able to withstand long dry periods by reducing water loss through small leaves, waxy surfaces and seeds that can persist until conditions improve. Glossopterids, for example, spread across the southern supercontinent, while early conifers adapt well to the drier northern and equatorial regions. In contrast, swamp-loving plants such as giant leucopsids and horsetails, once common in the Carboniferous coal forests, decline. The transition from coal swamps to open dry vegetation is another clear sign that aridity defines much of the Permian interior. Fires also shape the landscape, with long dry seasons and plants that produce abundant resin and litter wildfires become more frequent. Charcoal fragments preserved in rocks provide evidence of these ancient fires. Fire regimes influence ecosystems by clearing vegetation, recycling nutrients, and shaping plant communities. In the Permian, fires likely spread quickly across dry grass-like plants and shrubs, sparing only species adapted to regrow after burning. These patterns help explain why certain plant groups thrive while others vanish. Animal life on land also reflects the demanding conditions of the interior. Synapsids, including pelycosaurs early in the Permian and later therapsids, dominate terrestrial ecosystems. Many of these animals show adaptations to dry climates, such as sprawling postures for efficient movement across open ground and metabolic features that allow survival in extreme temperatures. Some grow large sails or crests which may help regulate body temperature by absorbing or releasing heat. The diversity of synapsids shows that despite harsh environments, animals continue to evolve ways of coping with heat dryness and seasonal extremes. The record of the Permian interior is also revealed in paleosols, which are ancient soils preserved in rock. These soils show features such as carbonate nodules, slickened sides from shrink-swell clays, and horizons rich in salts. Such characteristics are typical of soils in modern arid and semi-arid regions. By studying paleosols, scientists reconstruct rainfall, amounts, evaporation rates, and vegetation cover. The findings are consistent with a world where large areas receive little water and experience strong seasonal swings. The persistence of these arid landscapes across millions of years emphasizes how stable and widespread the climatic patterns of the Permian interior are. Unlike short-term droughts in modern times, the dry conditions of central Pangaea last for geologic spans with entire ecosystems and sedimentary systems built around them. This stability is tied to the geography of the supercontinent. As long as Pangaea remains intact, its interior remains cut off from moisture. Only tectonic breakup in later eras will eventually alter these patterns. The dryness of the Permian interior therefore defines both the rocks and the life of the time. It creates dunes that fossilize into cross-bedded sandstones basins filled with evaporites that form massive salt layers, red beds rich in iron, and soils that record low rainfall. It shapes plant communities that can withstand fire and drought, and it pressures animal groups to adapt or decline. The heart of Pangaea becomes one of Earth's largest deserts, lasting not for centuries or millennia, but for tens of millions of years. Its presence influences global climate by reflecting heat-generating dust and altering atmospheric circulation, while at the same time limiting the spread of lush vegetation and coal-forming swamps. The land that once held expansive forests and wetlands in earlier periods now gives way to dryness extremes and the persistent imprint of aridity. The climate of the Permian is not uniform, but instead displays striking contrasts between different regions and seasons. While the heart of Pangaea remains dry and continental, the coastal and near-coastal zones experience monsoonal rhythms that bring heavy seasonal rains, followed by long periods of dryness. Monsoons arise because land and sea warm at different rates. During the hot season, the interior of the continent heats rapidly, causing air above the land to rise. Moist air from the surrounding seas rushes in to replace it, and this moisture condenses into rainfall as it ascends. In the cool season, the process reverses with air sinking over the land and suppressing precipitation. In the Permian, this cycle plays out strongly in regions near the Tethys Ocean and the equatorial margins of the supercontinent. Sedimentary rocks from these zones preserve alternating layers of muds and sands that reflect seasonal flooding and drying. River channels cut through floodplains, leaving behind point bars and levees, only to dry out and shrink during the dry season. In some deposits, mud cracks show where shallow pools of water evaporated under intense heat, leaving polygonal patterns that later hardened into stone. Caliche horizons, which are layers of carbonate cement formed in soils by evaporation of groundwater, point to repeated wetting and drying cycles. These features together confirm that the climates of the monsoonal belts were highly seasonal, shaped by strong swings between moisture and drought. Vegetation in these regions responds to the rhythm of wet and dry seasons. Glossopterids in the south and early conifers in equatorial zones develop features that allow them to endure months of low water after bursts of growth during wet months. Leaf impressions from these plants are often preserved in fine-grained sediments that settled in quiet water during rainy intervals, then were buried under sands during floods. The growth rings of fossil wood also show variation between wide bands formed in favourable wet seasons and narrow bands formed during drought. These tree rings offer a clear signal of the intensity of seasonal contrasts during the Permian. Animals too are influenced by the monsoon cycle. Insects, which by this time are diverse and widespread, follow seasonal pulses of vegetation. Fossilized insect wings and tracks suggest that swarms were common during the rainy season, when plants provided abundant food, but they retreated during dry months. Amphibians, which still rely on water for reproduction, cluster in wetter lowlands, and may retreat into burrows or shaded refuges during drought. Their fossils are often found in deposits associated with ephemeral ponds and streams, indicating that their lives are closely tied to the seasonal hydrological cycle. Synapsids, including therapsids, adapt by developing more advanced metabolisms that allow them to remain active in fluctuating climates. Evidence for these seasonal cycles is not only preserved in sediments and fossils, but also in chemical signatures. Stable isotopes of oxygen in carbonate minerals vary with rainfall and evaporation. In monsoonal regions, alternating wet and dry intervals cause cyclical shifts in isotope ratios. These signals can be traced in Permian limestones, giving geologists a tool to reconstruct how intense and regular the monsoons were. Together with sedimentary structures and paleosols, the isotope evidence confirms that the climate of many parts of Pangaea was dominated by regular, predictable yet extreme seasonal contrasts. Beyond the equatorial belts, the pattern shifts again. At higher latitudes, winters are colder and summers milder, but even here the presence of a vast landmass creates sharp temperature swings compared to modern, ocean-moderated climates. Frost features in soils and glacial deposits in southernmost Gondwana show that polar regions still experience cold conditions, even as equatorial deserts swelter under heat. The contrast between poles and equator is strong, but overall the Permian world is warmer than earlier glacial periods. Ice sheets that once covered large parts of Gondwana during the Carboniferous diminish, leaving behind only scattered remnants by the Middle Permian. One striking effect of the monsoons is the creation of seasonal rivers that flow with great power when rains arrive. These rivers transport huge loads of sediment from highlands into basins. Thick deposits of sandstones with ripple marks and cross-bedding preserve the history of these floods. Fossilized channels show that rivers often change course, leaving behind abandoned meanders and floodplains covered with fine sediments. In some cases, large deltas form where rivers empty into inland seas, delivering nutrients that support bursts of productivity in aquatic ecosystems. But when the rains end, these systems dry, leaving behind cracked mud and stranded organisms. Such rhythms of boom and bust are recorded in the fossil record as communities appear in abundance in some layers and vanish in others. The role of atmospheric circulation in creating these contrasts can be understood through modern climate models applied to Permian geography. These models show that with Pangaea's immense land area, high summer temperatures create intense low-pressure zones over the continent. Winds from the Panthalassa and Tethys seas converge toward these lows, carrying moisture inland only as far as their strength allows. Beyond that distance, air masses are dry. During winter, the situation reverses and high-pressure zones over the cold land push air outward, suppressing rainfall. This seasonal pulse strengthens monsoons along coasts, but deepens drought in the interior. The alternation of winds explains why some regions experienced flooding and growth while others remained barren. Wildfire activity also connects to these seasonal extremes. Dry vegetation at the end of the rainy season becomes fuel for fires ignited by lightning strikes in thunderstorms or by spontaneous combustion of accumulated plant material. Charcoal layers in Permian sediments often alternate with flood deposits, showing that fires followed seasons of growth. These fires further reinforce the cycle by opening landscapes, reducing dense cover, and favouring plants able to recover quickly after burning. Fire is not simply a destructive force, but part of the ecological rhythm of the monsoonal landscapes. In the marine realm near these coastal zones, runoff from heavy rains delivers nutrients to shallow seas, driving short-lived blooms of productivity. Fossil assemblages of ammonoids, brachiopods, and foraminifera in certain layers reflect these pulses of nutrient input. Yet these benefits are temporary, and as dry seasons take hold, restricted circulation and high evaporation lead to stressed marine conditions, sometimes promoting the growth of evaporates along shorelines. Thus, the same seasonal contrasts that sustain bursts of life also create conditions of scarcity and stress. The alternating climates of the Permian reinforce the division between regions. While the central interior remains locked in long-term drought, coastal belts follow a cycle of rains and droughts, and high latitudes retain cold winters and shorter summers. The world of the Permian is one of sharp contrasts, all tied to the arrangement of land and sea and the physics of atmospheric circulation. Plants, animals, rivers, soils, and sediments all carry the marks of these seasonal extremes, leaving a record that is still visible to those who study the rocks of today. Across the vast interior of Pangaea, wind is a dominant force shaping the surface of the land. With little moisture-sparse vegetation and broad expanses of exposed sediment, the conditions allow sand and dust to be lifted and carried for great distances. Over millions of years, this process builds immense landscapes of dunes and dust plains. These arid features are not isolated but stretch across entire regions, leaving behind thick layers of rock that record their presence long after the dunes themselves are gone. When geologists walk through Permian formations today, they see towering cliffs of cross-bedded sandstone. Each angled layer is the frozen imprint of a dune slope that once shifted under strong winds. The geometry of these layers reveals the direction of prevailing winds, often consistent across large regions, showing that desert climates were stable and persistent for ages. The dune fields of the Permian, known as ergs, can be compared in size to the Sahara Desert of today, but they are often larger and longer lasting. Their surfaces are dominated by Bachan dunes, crescent-shaped ridges that migrate steadily, and by linear dunes that stretch for tens of kilometers. These forms arise as sand grains are pushed up the windward slope and cascade down the leeward side. The repetition of this simple process over endless years shifts entire landscapes. Sand seas become mobile systems, their crests slowly wandering across the land while maintaining the same overall character. The thickness of sandstone layers in Permian basins shows that these dunes endured not for centuries but for millions of years, preserving the evidence of a climate that seldom delivered enough rainfall to stabilize the surface with vegetation. Between the great dune systems lie regions where dust dominates. Fine silt carried aloft by winds sweeping over dry surfaces settles in thick blankets. These loess deposits accumulate, gradually forming plains of soft sediment that can extend across hundreds of kilometers. In some cases, dust carried from deserts settles in distant basins, creating layers far from its source. The presence of such deposits in Permian rocks demonstrates the strength and reach of the winds that cross the supercontinent. Loess is easily reworked by later erosion, yet where it survives, it speaks of atmospheres filled with suspended particles, reducing visibility and coating the land in fine powder. This dust not only reshapes the landscape, but also influences climate, as airborne particles reflect sunlight and alter atmospheric circulation. Evaporate basins add to the character of these dry environments. In low-lying depressions, water occasionally collects during rare storms or seasonal floods. With no outlet to the sea and high evaporation rates, the water quickly disappears, leaving behind crusts of salt and gypsum. Over time, these deposits build into thick layers, sometimes hundreds of meters deep, as cycles of flooding and evaporation repeat. In the Permian, some of the most extensive evaporate sequences in Earth's history are formed. They occur in areas such as the Delaware Basin of what is now North America and across parts of Europe and Asia. The scale of these deposits reflects the intensity of evaporation in a world where large parts of the supercontinent are cut off from moisture. The visual impression of the Permian interior would be one of striking color and brightness. Red beds spread across wide basins, their iron-rich soils baked under the sun. Sand dunes rise in pale and golden waves, shifting continually under persistent winds. Salt flats gleam under a cloudless sky, their surfaces white and harsh. Dust veils the horizon, carried high into the air by steady winds. Rivers appear only briefly, carving shallow channels and leaving behind lenses of sand that vanish into dry plains. For long stretches of time, much of the land is silent except for the sound of the wind moving sand and dust across an almost lifeless surface. Yet life does exist, adapted to these demanding settings. Plants anchor themselves along the margins of basins where water may briefly gather. Conifers and seed ferns hold on in sheltered zones, their roots probing deep for moisture. Their presence helps stabilize some surfaces, but is too sparse to halt the advance of dunes. Animals roam the open spaces, many of them synapsids, capable of enduring heat and dryness. Fossil trackways in Permian sandstones capture the moment when creatures crossed dunes, their footprints quickly buried and preserved by shifting sand. These tracks are sometimes the only evidence of life in landscapes otherwise dominated by wind and mineral. Dust itself leaves traces in the geologic record beyond the places it settles. When carried to the sea, it delivers nutrients such as iron, which can stimulate productivity in marine environments. This link between deserts and oceans plays a role in the global cycles of the Permian, connecting arid interiors with distant ecosystems. In addition, dust layers interbedded with marine sediments act as time markers, showing when storms swept across the land and carried particles far from their source. These connections illustrate how even the emptiest landscapes contribute to broader Earth systems. The endurance of these desert environments is confirmed by the thickness of the sedimentary successions they produce. In some regions, layers of cross-bedded sandstone evaporates and red beds reach thousands of meters. Each layer represents repeated cycles of dune migration, dust deposition, and basin evaporation. The sheer scale of these records tells scientists that the deserts of the Permian are not brief episodes but long-lasting regimes tied to the stable geography of Pangaea. Only major tectonic or climatic changes far beyond seasonal variation could alter such patterns. The processes that build and maintain these deserts also leave behind clues about atmospheric circulation. The orientation of ancient dunes indicates the direction of prevailing winds. By studying these orientations across continents, geologists reconstruct wind belts of the Permian atmosphere. The patterns often match what climate models predict for a world with a single vast landmass. Strong trade winds near the equator, westerlies at mid-latitudes and polar easterlies in high latitudes. The dunes of the Permian thus serve not only as testimony to aridity, but also as archives of wind systems that shape the global climate. As deserts expand and persist, they influence the evolution of life. Plants with drought-tolerant traits spread more widely, and animals with physiological or behavioral strategies for coping with heat and lack of water become dominant. Synapsids with efficient metabolisms thrive where amphibians decline. Fire-adapted plants secure niches where wildfires sweep across dry vegetation. These adaptations shape ecosystems that differ greatly from the swampy forests of the Carboniferous. The dominance of deserts pushes Earth's biosphere onto new paths with long-term consequences for the diversity of later eras. The deserts of the Permian therefore stand as a defining feature of the period. They are not scattered anomalies, but the prevailing condition across vast regions. They produce immense dune seas, dust plains, and evaporate basins that reshape the land. They leave behind vivid geological records in red beds, cross-bedded sandstones, and thick salt layers. They drive adaptations in plants and animals and feed back into global cycles through dust and evaporation. In every sense, the deserts are both a product of Pangaea's geography and a force that shapes the course of life and climate during the Permian. Across the wide interior basins of Pangaea, water collects only rarely, and when it does, the outcome is often the slow growth of thick mineral deposits, as evaporation removes the water and leaves behind solid layers of salts. These deposits are called evaporites, and they become one of the most characteristic signatures of the Permian world. They form when shallow seas or lakes cut off from free connection to the open ocean receive water inflow, but lose it faster through evaporation than they gain it. Over time, the dissolved minerals in the water, such as halite gypsum and anhydrite, precipitate and accumulate in repeating beds. In some places, cycles of flooding and drying repeat countless times, building successions hundreds of meters thick. These evaporites stretch across regions such as the Delaware Basin in what is now North America, the Zechstein Basin in Europe, and similar low-lying areas elsewhere. Their sheer scale tells us that evaporation in the Permian is not occasional, but continuous, driven by long dry seasons, intense sunlight, and little replenishment of water. The appearance of these deposits creates distinctive landscapes. Salt flats cover the ground with bright reflective crusts gleaming under the sun and creating heat shimmer in the air. Beneath the crust, brines linger until the last moisture is gone, leaving behind polygonal cracks as the salt contracts and dries. When dust blows across these flats, it mixes with the white crust to form layers of alternating colors. Each new flood brings fresh dissolved minerals that once evaporated form a new bed. Over millions of years, these beds are compressed into rock, building the enormous evaporate formations that geologists see today. Their presence is evidence of a hydrological cycle that is harsh, limited, and unable to sustain permanent bodies of water across much of the supercontinent. In addition to evaporates, another widespread feature of Permian basins is the deposition of red beds. These are sediments rich in iron that oxidizes when exposed to the atmosphere, giving the rocks a characteristic red or brown hue. Red beds form when soils and sediments remain open to air under dry conditions, allowing oxygen to react with iron minerals. They indicate not only aridity, but also an environment where standing water is rare and organic material is scarce. Across much of Pangaea, thick sequences of red sandstones, siltstones, and shales record the prevalence of these dry surface conditions. The consistency of red beds across continents is one of the strongest signs that the interior of Pangaea was dominated by open, oxidized landscapes rather than humid, waterlogged ones. Together, evaporates and red beds provide complementary signals of the climate. Evaporites show that water occasionally gathered in closed basins, but evaporated quickly, while red beds reveal that in surrounding uplands and plains, soils were persistently dry and oxygen-rich. These deposits also preserve signs of processes that acted within them. In some evaporate layers, delicate crystals of halite and gypsum are preserved, indicating that evaporation was rapid enough for crystals to grow before being buried. In red beds, fossil soil horizons appear sometimes with carbonate nodules that form in dry soils as groundwater evaporates. Each feature is a small clue to the wider pattern of dryness that prevailed. Loess deposits made of fine wind-blown silt add another piece to the picture. They are especially common downwind of desert regions where dust was lifted into the atmosphere and carried across distances. The accumulation of loess creates soft, fine-grained layers that are often uniform in texture and structure. These deposits are important not only because they show the presence of strong winds and dust storms, but also because they help track prevailing wind directions. In some areas, thick loess blankets cover older sediments, indicating prolonged phases when the atmosphere was filled with suspended dust. This dust would have had effects beyond the land surface. By scattering sunlight and cooling the ground during the day while trapping heat at night, it altered temperature patterns locally, and by fertilizing marine waters with minerals such as iron, it influenced ocean productivity far from its source. The presence of evaporates and red beds also reflects how restricted circulation in certain marine basins became during the Permian. Where shallow seas were partly enclosed, evaporation concentrated salts faster than open water could dilute them. This effect was especially strong in the Zechstein Basin of Europe, where repeated transgressions of the sea flooded shallow depressions, only to retreat and evaporate again, leaving one of the thickest and most complete evaporate sequences in Earth's history. The cycle repeated many times, creating an alternating rhythm of marine limestone, gypsum, halite, and red shale. The repetition in these layers reveals that the processes driving them were stable and long-lasting. From a geochemical point of view, these deposits also provide important markers. The chemistry of halite, gypsum, and associated minerals preserves information about the composition of ancient seawater. Variations in sulfur and strontium isotopes within evaporates allow scientists to reconstruct changes in global cycles of these elements. Red beds, through their iron content, likewise record the oxidation state of the atmosphere. Combined, these deposits confirm that the Permian world is one of widespread oxidizing conditions at the surface, limited standing water, and strong evaporation across continents and shallow seas. The ecological implications of these environments are significant. Plants and animals in regions dominated by evaporates and red beds face limited water and soil fertility. Vegetation is sparse, consisting mainly of drought-tolerant species such as conifers and seed ferns that can survive on limited groundwater. Animal fossils in these regions are fewer than in wetter settings, but when they appear they often represent creatures adapted to harsh conditions such as synapsids, capable of regulating their body temperature and conserving water. Trackways preserved in red sandstone suggest that animals moved across dry floodplains and dune margins in search of resources, leaving fleeting impressions quickly buried by sand or dust. The persistence of such environments for millions of years means that ecosystems are shaped by scarcity as much as by abundance. Unlike coal-forming swamps of earlier times where lush vegetation and standing water supported dense communities, the evaporate and red bed landscapes of the Permian are defined by limits. Fires sweep across dry vegetation, dust coats the land, and salt pans restrict growth. Yet within these constraints, life endures, finding ways to exploit brief windows of moisture or to survive long droughts. The balance between dryness and survival defines the biosphere of these interior basins. Geologists piecing together this record see not only the visible deposits, but also the patterns that connect them. Evaporates, red beds, loess, and paleosols align to tell the same story that the supercontinent's geography, produces climates of great aridity where evaporation exceeds precipitation and where oxygen-rich soils dominate. The size and persistence of these features across many regions make it clear that they are not local anomalies but continental-scale conditions lasting for much of the Permian. As tectonic plates remain locked together in the supercontinent, these conditions endure, marking one of the most prolonged dry intervals in Earth's history. The legacy of evaporates and red beds is that they remain today as some of the thickest, most continuous stratigraphic records from the Permian. They are studied not only for what they reveal about climate and life, but also because they contain resources such as salt potash and gypsum used by human societies. In their origin, however, they are reminders of the vast deserts and drying basins that once covered the heart of Pangaea. Each layer of salt and red sandstone is a message from an ancient landscape where water vanished, winds carried dust, and the sun baked the ground without relief. Along the edges of the great supercontinent where land meets the sea, another world develops very different from the deserts and evaporate basins of the interior. Here in warm, shallow waters, carbonate platforms and reefs grow, creating some of the most biologically rich environments of the Permian. These structures are built primarily from the skeletons of organisms that extract calcium carbonate from seawater, including sponges, algae, bryozoans, and calcareous microbes. Together they form vast reefs that line continental margins, shelf seas, and the edges of the Tethys Ocean. These reefs are not small or local, but in some regions they extend for hundreds of kilometers, creating thick accumulations of limestone that record their steady growth over millions of years. The conditions that allow reefs to flourish are a direct consequence of geography and climate. The shallow waters of continental shelves provide stable platforms where sunlight can penetrate, essential for photosynthetic symbionts that live within some reef organisms. Warm temperatures and clear water encourage carbonate precipitation, while steady circulation brings nutrients. Unlike the evaporate basins of the interior, these coastal margins are zones of abundance where life multiplies. Fossil assemblages show an extraordinary diversity with reef frameworks crowded by sponges encrusting algae, fusulinid foraminifera, and a wide variety of brachiopods and mollusks. These organisms form complex ecosystems with niches for filter feeders, grazers, and predators. Fusulinids, a group of large foraminifera, are especially prominent in early Permian reefs. Their shells, sometimes as large as a fingernail, accumulate in great numbers, contributing significantly to carbonate sediment. Because they are widespread and evolve rapidly, fusulinids are useful to geologists as index fossils, allowing precise correlation of Permian rock layers across distant regions. Ammonoids also thrive with coiled shells that display intricate suture patterns. Their rapid diversification in reefal and nearshore environments reflects the productivity of these settings. Sponges, both siliceous and calcareous, form important structural elements of the reefs, binding sediments together and providing habitat for other organisms. The presence of bryozoans and corals adds to the variety, though the dominant reef builders of this time are sponges and algae, rather than the corals that dominate later eras. The structure of a reef is complex. At the seaward edge lies a high-energy zone where waves crash, breaking and reworking carbonate material. Behind this crest, protected lagoons host calmer waters with diverse communities of organisms. Seaward slopes accumulate debris shed from the reef, forming thick talus deposits that build outward over time. The result is a layered body of limestone that preserves a detailed record of reef growth and collapse. In some regions, successive reef complexes stack one upon another, separated by layers of shale or evaporate that indicate interruptions in reef growth. These interruptions often correspond to changes in sea level climate or ocean chemistry. Sea level plays a crucial role in reef development. During times of relative stability or gradual rise, reefs can keep pace with the sea growing upward and outward. But when sea level falls rapidly, reefs are exposed and die, leaving behind erosional surfaces. Evidence of such cycles appears repeatedly in Permian carbonate sequences, where abrupt shifts from reef limestone to red beds or evaporites reveal transitions from shallow seas to exposed land or restricted basins. These cycles reflect the dynamic interaction between tectonic activity climate and eustatic sea level change. Chemical signatures preserved in reef carbonates also provide insight into global processes. The ratios of carbon isotopes within limestone record fluctuations in the carbon cycle, including periods of high organic productivity and times of stress. Oxygen isotopes capture changes in temperature and evaporation. Together, these signals allow scientists to reconstruct not only the local environments of reefs, but also the larger-scale climate trends of the Permian. The records show intervals of relative stability, punctuated by disruptions that foreshadow the environmental stresses of the late Permian. Despite their success, reefs of the Permian face challenges. Restricted circulation in some basins leads to episodes of anoxia when bottom waters lack oxygen. These events are recorded by layers of black shale interbedded with reef limestone. In such intervals, reef communities decline or collapse, replaced by deposits of fine muds that show life was greatly reduced. In addition, evidence suggests that shifts in ocean chemistry, such as increased levels of dissolved carbon dioxide at times, make conditions unfavorable for carbonate precipitation. The repeated pattern of reef growth collapse and recovery indicates that these ecosystems are sensitive to changes in both physical and chemical conditions. The decline of Permian reefs becomes especially pronounced toward the end of the period. While early and middle Permian reefs are extensive and thriving, late Permian reef systems shrink and disappear in many regions. Fossil evidence shows that sponge-dominated communities once widespread vanish abruptly. Fusulinids once abundant also decline sharply. The reasons for these losses remain under study, but they are linked to changes in ocean circulation, rising carbon dioxide, and reduced oxygen in marine waters. By the close of the Permian Reef, ecosystems collapse almost entirely, and they do not return to their former complexity until long into the Mesozoic. For much of the Permian, however, reefs provide stable and productive habitats that contrast strongly with the arid conditions inland. They are centers of biodiversity, supporting a web of organisms that interact in intricate ways. They also serve as carbon sinks, locking away calcium carbonate in thick sequences of limestone. In doing so, they influence global carbon balance, contributing to the regulation of climate and ocean chemistry. The reefs thus play both local and planetary roles, shaping ecosystems and Earth systems alike. The remains of these reefs, preserved as limestone cliffs and mountains, are among the most striking legacies of the Permian. In places such as the Guadalupe Mountains of North America, towering exposures of reef limestone display cross-sections of entire reef complexes from crest to slope to basin. These outcrops allow modern scientists to study in detail the processes that built and destroyed reefs, revealing the rhythm of growth and collapse across millions of years. They stand as enduring monuments to ecosystems that once thrived in warm, shallow seas before yielding to the environmental upheavals of the Permian. The story of reefs in the Permian is therefore one of abundance followed by vulnerability. They begin as flourishing systems along the edges of Pangaea, build massive carbonate platforms that shape continental margins and support diverse marine communities. Yet they remain sensitive to the balance of climate chemistry and circulation, and when those balances tip, the reefs falter. Their rise and fall illustrate both the vitality of life under favourable conditions and its dependence on environmental stability. The same supercontinent that creates deserts inland also frames the seas where reefs grow, linking the dry land and the wet margins in a single global system whose dynamics will eventually bring stress to both. The oceans of the Permian are shaped by the arrangement of continents and the presence of one dominant body of water, the Panthalassa Ocean, which stretches across most of the globe. Its vastness makes circulation patterns different from those of later eras with several smaller oceans. Instead of numerous currents weaving between continents, there is one major system of gyres and deep water flows influenced strongly by the boundaries of Pangaea. Along the western margin of the supercontinent, currents sweep north and south with little obstruction, while in the enclosed Tethys Ocean to the east, water circulates more slowly and becomes prone to restriction. These differences play a critical role in determining which regions of the sea remain well oxygenated and which slide into stagnation. In open Panthalassa, surface currents move quickly, driven by winds and temperature contrasts distributing heat across vast distances. This helps maintain relatively stable surface conditions where plankton and nekton can thrive. Ammonoids, fish, and other marine organisms fill the surface waters, while productivity remains steady in equatorial zones. But beneath this lively surface lies a different story. Deep waters cut off from circulation in many places do not receive fresh oxygen from above. Without overturning currents to mix the layers, these waters become depleted in oxygen. When organic matter sinks from the surface and decays, it consumes what little oxygen remains. Over time, large regions of the deep ocean become anoxic, meaning that they lack oxygen entirely. The evidence for this is found in black shales deposited in many Permian basins. These shales are rich in organic carbon preserved because the lack of oxygen prevents decay by most organisms. They often contain laminations that remain undisturbed, showing that burrowing animals were absent. Such deposits tell scientists that the seafloor was inhospitable for much of the Permian, with life confined to the upper layers of the water column. In some cases, chemical evidence indicates not only anoxia, but euxemia, a condition in which hydrogen sulfide accumulates, making the waters toxic. These conditions likely developed first in restricted basins such as those connected to the Tethys, but eventually spread more widely, contributing to stresses on marine ecosystems. The stratification of the ocean, meaning the separation of water layers that do not mix easily, is a central factor in this pattern. Warm, salty waters at the surface resist mixing with cooler, denser waters below. The absence of strong polar currents in the Permian also reduces overturning circulation. Modern analogues such as the Black Sea provide a small-scale example of how such conditions can develop with surface waters supporting life, while deep layers remain poisonous. In the Permian, however, the scale of these stagnant waters is far greater, covering entire basins for millions of years. The consequences for marine life are profound. Reef systems and carbonate platforms thrive only in shallow, well-circulated waters where oxygen is sufficient and nutrients are replenished. But in deeper basins, diversity is limited. Brachiopods, ammonoids, and foraminifera may flourish in shallower shelves, yet their fossils disappear in black shale sequences, replaced by fine laminations of mud. This uneven distribution of life creates a patchwork world, with some regions full of abundance and others nearly barren. It also makes marine ecosystems vulnerable to shifts in circulation or chemistry that could expand anoxic zones. Isotopic records in marine carbonates reveal cycles of change in the global carbon system during the Permian. Variations in the ratio of carbon isotopes reflect shifts between times when organic carbon burial was high, drawing down carbon dioxide, and times when burial was low or oxidation returned carbon dioxide to the atmosphere. These cycles may be linked to changes in ocean stratification and anoxia, as more widespread anoxic conditions can lead to greater preservation of organic matter. Sulfur isotopes from evaporites and marine sulfates provide additional clues, recording changes in the balance of sulfate reduction and sulfide burial. Together, these records show that the chemistry of the ocean is dynamic, with long-term trends that influence both marine life and the global climate. Circulation in the Tethys Ocean adds complexity. Unlike Panthalassa, which is open and vast, the Tethys is semi-enclosed between the arms of Pangaea. This means water exchange with the open ocean is limited. As a result, circulation in the Tethys can become sluggish, and episodes of restricted oxygenation are more common. Fossil evidence from Tethyan basins shows alternating intervals of rich, diverse marine communities and intervals of decline marked by black shales and reduced diversity. The shifts between these states reveal how sensitive these seas were to changes in climate, sea level, and global circulation patterns. One additional influence is the contribution of dust and nutrients from the arid interior of Pangaea. Winds carry fine particles rich in minerals into the oceans where they fertilize surface waters. This promotes bursts of productivity in planktonic communities, which in turn support ammonoids and other higher organisms. Yet the decay of this organic matter also draws oxygen from deeper waters, reinforcing stratification and expanding anoxic zones. The same process that stimulates life at the surface can therefore create death below. This feedback underscores how interconnected land and sea systems are during the Permian. The long-term persistence of ocean stratification in the Permian suggests that these conditions are not isolated events, but sustained states tied to continental arrangement and climate. As long as Pangaea remains with its vast interior deserts, and limited polar sea circulation patterns are unlikely to change dramatically. This stability allows anoxic basins to endure for millions of years, shaping the evolution and distribution of marine organisms. Groups that can tolerate low oxygen conditions gain advantages, while others remain confined to better circulated shelves. In some regions, carbonate platforms and reefs act as partial barriers restricting water movement and further encouraging stagnation in basins behind them. The accumulation of thick carbonate sequences alongside black shales demonstrates how close abundance and scarcity can exist. On one side of a reef, ecosystems flourish in well-lit oxygenated waters. On the other side, dark anoxic basins record absence and decline. These sharp boundaries preserved in the rock record show how physical geography and circulation structure entire marine worlds. By examining the sediments and isotopes of the Permian, scientists reconstruct a picture of oceans divided into zones of prosperity and stress. Circulating surface currents sustain rich life, reefs build carbonate mountains, and plankton fuel ecosystems above. But beneath lies a shadow world of stagnant waters where decay consumes oxygen and sulfide poisons accumulate. The interaction of these zones creates cycles of expansion and contraction, balance and imbalance that echo through the geological record. They set the stage for the vulnerabilities that will later play a role in the largest extinction in Earth's history, though for much of the Permian life continues to adapt within the limits imposed by circulation and stratification. As circulation patterns shape the global ocean of the Permian, one of the most striking developments is the growing presence of oxygen-poor and toxic conditions in deeper waters. The evidence for these conditions is written in the rock record with unusual clarity. Layers of black shale that stretch across wide regions tell of seas where life could not thrive at the bottom. These dark deposits contain high amounts of preserved organic matter, laminated structures with no sign of burrowing animals and chemical signatures that point to a lack of oxygen. In some cases, the chemistry indicates not only anoxia, which is the absence of oxygen, but euxinia, where hydrogen sulfide builds up to toxic levels. Together, these signs show that large parts of the Permian Ocean are hostile to life below the surface. The processes that lead to such conditions begin at the surface. Plankton and other organisms bloom in nutrient-rich waters, especially when winds carry dust and minerals from the arid interior of Pangaea into the sea. These blooms increase productivity and feed larger animals such as ammonoids and fish. But when this organic material sinks, it decays, consuming oxygen in the lower water layers. If circulation is weak and deep waters are not replenished with oxygen from above, the balance tips toward depletion. Once oxygen is gone, microbes that reduce sulfate take over, releasing hydrogen sulfide. This gas is deadly to most animals, and it changes the chemistry of the water and sediments. When preserved in the rock record, these oxinic conditions leave behind unusual mineral assemblages such as pyrite formed from sulfide reactions. The scale of anoxia and euxinia in the Permian is remarkable. Modern seas such as the Black Sea show how stratified waters can remain oxygenated at the top, while stagnant and sulfide-rich below. In the Permian, entire basins are thought to have behaved this way for millions of years. The lack of burrows in black shales indicates that benthic life could not survive. Fossil assemblages show sharp differences between shallow shelf environments, where brachiopods, bryozoans and sponges flourish, and deep basins where diversity collapses. This uneven distribution of life creates ecosystems that are fragile and easily disrupted when anoxic waters expand toward shallower regions. Chemical evidence from isotopes supports this interpretation. Shifts in sulfur isotopes in marine sulfates indicate widespread bacterial sulfate reduction, consistent with euxinic waters. Carbon isotopes record fluctuations that match intervals of expanded anoxia when organic carbon burial increases. Trace metals such as molybdenum and uranium, which accumulate under oxygen-poor conditions, are enriched in black shale layers. These geochemical signatures align across continents, confirming that anoxia is not a local phenomenon, but a global trend. The expansion of anoxia and euxinia has significant consequences for marine ecosystems. Many groups of organisms depend on stable oxygen-rich conditions. Reef communities, which rely on symbiosis and steady carbonate precipitation, collapse when nearby waters turn toxic. Fusulinid foraminifera once widespread decline rapidly in regions affected by low oxygen. Ammonoids, though more mobile, also suffer during intervals of widespread euxinia. Meanwhile, organisms with tolerance for stressed conditions persist longer. This selective pressure shapes the evolutionary paths of marine life during the late Permian, with some groups disappearing entirely and others reduced to narrow ecological niches. Sedimentary structures reveal that these episodes of anoxia often follow transgressions when sea levels rise and flood continental margins. Rising seas create new shallow basins and restrict circulation, promoting stagnation. At the same time, they bring nutrients onto shelves, fueling productivity and driving oxygen demand. The combination of nutrient input and restricted circulation is especially potent in creating low oxygen conditions. The alternation of carbonate-rich layers with black shales in many Permian sequences reflects these cycles of flooding, productivity and stagnation. The persistence of anoxic and euxinic waters is linked to the arrangement of Pangaea. With such a vast single landmass, polar currents that might otherwise drive deep circulation are limited. Panthalassa, though immense, lacks the strong overturning currents seen in later oceans. Instead, stratification remains stable, allowing oxygen-poor conditions to persist. This stability means that once anoxic conditions are established, they are difficult to reverse without major climate or tectonic changes. One striking example of the ecological impact of anoxia comes from reef systems. Early in the Permian, reefs are extensive and diverse, but by the late Permian many are reduced or eliminated in regions where black shales dominate the stratigraphy. The collapse of sponge-dominated reefs is closely tied to an expansion of euxenia in surrounding seas. This pattern suggests that toxic waters encroached on formerly habitable shelves, undermining ecosystems that had thrived for millions of years. The effect is not limited to marine organisms. The chemistry of the atmosphere and the land can also be influenced. When hydrogen sulfide escapes from the ocean surface during strong upwelling events, it can rise into the atmosphere, potentially damaging the ozone layer and exposing land organisms to harmful ultraviolet radiation. Some scientists propose that such processes played a role in stressing terrestrial ecosystems near the end of the Permian. While this idea remains debated, it highlights the possible connections between ocean chemistry and the broader biosphere. The record of anoxia is uneven, showing intervals when conditions worsened and intervals of partial recovery. These cycles suggest that climate shifts, volcanic inputs, and sea level changes influence the spread of low oxygen waters. Yet the overall trend across the Permian is toward more frequent and widespread anoxia, particularly in the late stages of the period. This progression sets the stage for the extreme environmental crises of the final Permian extinction, when these conditions reach their most destructive extent. From a reflective standpoint, the evidence of anoxia in the Permian underscores the vulnerability of marine systems to imbalances between productivity and circulation. Life in the ocean thrives only when oxygen is supplied as quickly as it is consumed. When geography and climate interfere with that balance, vast regions can turn hostile. The rocks of the Permian show that such changes can endure not for decades or centuries, but for millions of years, reshaping ecosystems on a global scale. The expansion of anoxic and euxinic waters is therefore both a product of Earth's geography and a force that influences evolution and extinction. It links the deserts of the interior, which supply dust and nutrients, to the collapse of marine ecosystems, which cannot withstand the spread of toxic conditions. In every layer of black shale, in every absence of burrows or benthic fossils, there's a record of seas turned hostile by the slow, steady processes of circulation, productivity, and stagnation that characterize the Permian world. On land, the vegetation of the Permian is shaped by the same climatic forces that dominate the deserts and monsoons of Pangaea. Plants must contend with extended dry seasons, high evaporation, and soils that often lack water for long stretches of the year. As a result, the flora of the Permian looks different from the coal-forming swamps of the Carboniferous that came before. Giant lycopsids and tree ferns decline, while seed-bearing plants become the dominant forms. These include seed ferns such as Glossopteris, which spread widely across Gondwana, and conifers, which take hold in northern and equatorial regions. Their success reflects an evolutionary advantage. Seeds can survive periods of drought, allowing plants to reproduce even in unstable climates where spores would fail. Glossopterids form extensive forests across the southern continents, their tongue-shaped leaves preserved in great abundance in rocks of South America, Africa, India, and Antarctica. These plants are especially well adapted to cooler but still seasonal climates where wet and dry cycles alternate. Their broad leaves gather sunlight efficiently, and their root systems anchor them in soils that may dry between rainy periods. The widespread distribution of Glossopteris fossils provides one of the strongest pieces of evidence for the existence of Gondwana as part of the southern arm of Pangaea, since the same species appear across lands that are now separated by oceans. In equatorial and northern latitudes, early conifers gain prominence. Unlike the dense, swamp-loving vegetation of earlier times, conifers produce narrow leaves shaped like needles, which reduce water loss. Their seeds are encased in cones, providing protection and delaying germination until conditions are suitable. These adaptations allow conifers to thrive in dry uplands and seasonal lowlands. Fossil wood from Permian conifers shows growth rings that alternate between wide and narrow bands, reflecting the alternating abundance of wet and dry seasons. Such growth patterns mirror the climate extremes of the time and show that these trees endured repeated cycles of stress. Seed ferns other than Glossopteris also remain significant, especially in regions that are too dry for swamp forests, but not fully desert. These plants show a diversity of leaf shapes and reproductive strategies, some with seeds attached directly to leaves. Their persistence highlights the transitional nature of Permian vegetation, bridging the gap between older spore-based floras and the dominance of true seed plants that will follow in later eras. Shrubby growth forms and small trees are common, indicating that open woodland and savanna-like environments replace the closed canopy swamps of the Carboniferous. Coal formation becomes rare in the Permian as the climatic conditions needed for vast peat swamps disappear. Coal seams of Carboniferous age give way to red beds, evaporites and sandstones, all markers of dryness. Where coal does appear, it is limited to regions near coastlines or areas with exceptional local moisture. This decline in coal swamps has major consequences for both ecosystems and the global carbon cycle. With fewer swamps to bury organic matter, less carbon dioxide is drawn from the atmosphere, reinforcing the tendency toward warm, dry climates. The forests that remain are patchy, more resistant to fire, and less able to sequester carbon on a massive scale. Wildfire becomes an increasingly important factor in shaping terrestrial vegetation. Charcoal fragments preserved in Permian sediments show that fires are frequent and widespread. Seasonal dryness allows plant litter to build up, and lightning ignites fires during stormy transitions between wet and dry seasons. These fires clear vegetation, open landscapes, and favor plants that can regrow quickly or withstand burning. Many conifers show adaptations that allow them to recover after fire, such as thick bark and the ability to release seeds in response to heat. The cycle of fire adds another layer of stress and renewal to the ecosystems of the Permian, reinforcing the dominance of plants that can endure disturbance. The spread of these seed-bearing plants also creates new opportunities for animals. Forests of Glossopteris and conifers provide shelter and food for synapsids and reptiles that browse on leaves and seeds. Insects diversify alongside them, with groups such as beetles and early true bugs appearing in the fossil record. Pollination at this time is still largely wind-driven, but interactions between plants and insects begin to grow more complex, setting the stage for later evolutionary developments. The landscapes of the Permian are therefore mosaics of desert dunes, dry woodlands, fire-shaped conifer forests and seasonal wetlands, each with its own characteristic plant communities. Evidence for these vegetation patterns comes not only from leaf fossils and wood, but also from spores and pollen preserved in sediments. Palynology. The study of microscopic plant remains provides detailed records of which plants lived in which regions. Permian pollen assemblages shift towards seed plant dominance, with conifer and glossopterid pollen replacing spores of lycopsids and ferns. These microscopic grains are durable and travel widely, making them excellent indicators of vegetation change across the supercontinent. Their abundance confirms that seed plants are the backbone of terrestrial ecosystems during this period. The decline of swamp floras and the rise of drought-tolerant plants are also reflected in soils. Paleosols of the Permian often show carbonate nodules and root traces of woody plants rather than the waterlogged features of earlier coal swamps. These soils reveal that vegetation cover is thinner and more adapted to dryness, with roots penetrating deeper in search of water. The shift in soil properties across many regions is a clear sign that landscapes dominated by waterlogged forests have been replaced by drier open systems. The ecological consequences of this transformation are significant. With fewer dense swamps, habitats for amphibians shrink, and reptiles and synapsids expand into the open woodlands. Fire-tolerant plants and drought-resistant seed producers dominate, reducing the diversity of wetland floras. Carbon burial declines, changing the long-term balance of atmospheric gases. The very structure of ecosystems shifts from closed humid canopies to open fire-prone and seasonal landscapes. This shift does not occur suddenly, but unfolds steadily across the Permian as climates dry and the geography of Pangaea reinforces continentality. The legacy of Permian vegetation is clear in the fossil record. Glossopteris forests in Gondwana, conifer-dominated uplands in Laurasia, and scattered seed fern woodlands across the supercontinent testify to the resilience of plants in the face of drying climates. Their adaptations mark a turning point in botanical history. Seeds, tough leaves, and fire tolerance become the key strategies for survival strategies that will carry plants forward into later eras. The coal forests of the Carboniferous fade into memory, replaced by the drought-adapted landscapes of the Permian. The animal life of the Permian is dominated by synapsids, the lineage that will one day give rise to mammals, though in this era they appear in forms very different from anything familiar today. Early in the Permian, large sail-backed synapsids such as Dimetrodon and Adaphosaurus are common across the lowlands of North America and Europe. These animals, with sprawling limbs and long tails, carry tall bony spines along their backs, likely covered with skin to form sails. The sails may have played a role in regulating body temperature by absorbing heat in cool mornings and releasing it in hot afternoons. Whatever their function, these animals represent the first great expansion of synapsids into dominant roles in terrestrial ecosystems. Dimetrodon is a predator feeding on fish amphibians and smaller reptiles, while Adaphosaurus is a plant-eater with specialized teeth and jaws for grinding vegetation. Their presence together illustrates the breadth of ecological roles filled by synapsids even early in the period. As the Permian progresses, the synapsids diversify further into a group known as therapsids, which show more advanced features that foreshadow the mammalian condition. Therapsids develop more upright postures, differentiated teeth and larger temporal openings in the skull that allow stronger jaw muscles. These features give them advantages in feeding and movement, making them more versatile and efficient than their pelycosaur relatives. Therapsids quickly radiate into many ecological niches. Some, such as dinocephalians, grow to large sizes with thickened skull bones that may have been used in head-to-head pushing contests. Others, such as dicynodonts, become specialized herbivores with beak-like mouths and tusks. Dicynodonts spread widely and become some of the most successful plant-eaters of the late Permian, ranging from small burrowers to animals the size of cattle. Among predators, Gorgonopsians stand out. These therapsids possess long, saber-like canine teeth and agile bodies suited for hunting. They are among the top carnivores of the late Permian, preying on large herbivores such as dicynodonts. Their skulls and teeth reveal adaptations for delivering powerful bites, while their limb structure suggests they could move more quickly than earlier synapsids. Alongside them are therocephalians, a group of smaller predators with varied diets that include insects, small reptiles, and amphibians. The diversity of predatory therapsids shows that synapsids are not only numerous, but also ecologically dominant, occupying the role of apex hunters as well as mid-level carnivores. Reptiles also diversified during the Permian, though they remain overshadowed by synapsids, early relatives of archosaurs. The lineage that will later produce crocodiles, pterosaurs and dinosaurs appear in modest forms. Parasaur, large herbivorous reptiles with bony knobs on their skin, roam in some regions browsing on low vegetation. Captorhinids, smaller reptiles with multiple rows of teeth, specialize in feeding on tough plants. These reptiles contribute to the complexity of ecosystems, but do not surpass the synapsids in abundance or variety. The Permian is therefore a time when the ancestors of mammals dominate the land more than the ancestors of reptiles and birds. Amphibians, once abundant in the coal swamps of the Carboniferous, decline in the drier world of the Permian. Still, some lineages persist in wetter regions and river valleys. Temnospondyls, large amphibians with crocodile-like bodies, survive in pools and streams, preying on fish and small vertebrates. Their fossils show that they retain a significant presence in aquatic habitats, though they are less dominant on land. The reduction of swamps and wetlands limits their range, and they never again reach the ecological prominence they once held. The spread of synapsids and therapsids is closely tied to the changes in vegetation. As coal swamps vanish and open woodlands spread, herbivorous animals must adapt to tougher, drier vegetation. Dicynodonts and parasaurs develop jaws and teeth suited to grinding seeds and fibrous plant matter. Their success reflects how ecosystems reorganize around new sources of food. Carnivorous therapsids adapt in turn, developing stronger jaws and more agile bodies to pursue these new herbivores. The interdependence of plants and animals drives the evolutionary changes visible in the fossil record. Fossil trackways provide a vivid picture of how these animals moved across the land. Preserved in sandstones and mudstones, the tracks of therapsids and other vertebrates show patterns of gait and posture. Many therapsids walk with limbs held partly beneath the body, suggesting a shift toward more efficient locomotion compared to the fully sprawling gait of earlier synapsids. These changes foreshadow the fully upright posture of mammals, but remain distinctively Permian in form. Some track sites reveal evidence of social behavior with multiple individuals moving together across floodplains. While it is difficult to infer group structure with certainty, such trackways hint that some synapsids may have lived in herds or packs. The fossil record also preserves evidence of burrowing behavior. Some small dicynodonts and therocephalians are thought to have dug burrows for shelter from heat and dryness. These underground refuges would provide protection from predators and extreme climates, showing yet another way in which animals adapted to the challenges of the Permian world. In some cases, burrows contain the remains of multiple individuals, suggesting that parental care or group sheltering may have existed in these species. The global spread of synapsids and therapsids is confirmed by fossils found on every continent of Pangaea. From South Africa to Russia to North America, similar groups appear, reflecting the interconnected nature of ecosystems across the supercontinent. Regional variations exist, with certain groups more abundant in Gondwana and others in Laurasia, but overall the continuity of faunas demonstrates how unified the land was during this time. This broad distribution provides geologists and paleontologists with important tools for correlating rock layers and reconstructing ancient environments. The dominance of synapsids in the Permian marks a turning point in the history of vertebrates. For the first time, animals with more advanced metabolisms, differentiated teeth, and semi-upright gaits control the land. Their adaptations to dryness, fire, and open landscapes reflect the broader transformation of Earth's climate and ecosystems. While amphibians and reptiles continue to play roles, it is the synapsids, particularly the therapsids, that define the Permian biosphere. Their evolutionary experiments set the stage for future developments, even though many lineages will not survive the crises at the end of the period. The picture that emerges is one of diverse and dynamic animal communities spread across deserts, woodlands, and seasonal rivers. Large predators stalk herbivore herds, small burrowers scratch out lives in the soil, and amphibians linger in the remaining pools and streams. Insects buzz among the conifers, pollinating plants and feeding reptiles. The land of the Permian is alive with movement shaped by the constant pressures of heat, drought, fire, and evolving vegetation. The animals that inhabit this world are products of adaptation to a landscape that is often harsh, but filled with opportunity for those capable of enduring its extremes. The seas of the Permian, though stressed by stratification and episodes of anoxia, still host a wide range of organisms that together build rich marine assemblages. These communities differ from the coral-dominated reefs of later eras, but they are nonetheless diverse and complex. In warm, shallow waters, brachiopods remain highly abundant, their shells carpeting the seafloor in dense beds. They filter feed from the currents, attaching themselves to hard substrates or clustering together in great numbers. Alongside them, bivalve mollusks occupy similar roles, burrowing into soft sediments or attaching to reef surfaces. Their shells are preserved in immense quantities, leaving behind limestone layers composed almost entirely of skeletal fragments. Ammonoids, coiled cephalopods related to modern squid and octopus, are among the most dynamic members of the marine world. They swim freely in the water column, using jet propulsion to move and tentacles to capture prey. Their shells record intricate suture patterns that become more complex through the Permian. These patterns provide paleontologists with detailed markers for dividing and dating rock layers, since ammonoids evolve quickly and are widely distributed. Their presence in many marine deposits shows that even as deeper waters become hostile, surface waters still support thriving nectonic ecosystems. Fusulinid foraminifera are another hallmark of Permian seas. These single-celled organisms construct large shells, sometimes reaching several centimeters in length, remarkable for their complexity. They build chambers within their shells in intricate patterns that vary between species. Because they are so abundant and geographically widespread, fusulinids also serve as index fossils, helping to correlate Permian rocks across continents. In many limestone formations, fusulinid shells accumulate to such an extent that entire rock beds are composed primarily of their remains. Their extinction near the end of the Permian marks one of the clearest signs of the growing crisis in marine ecosystems. Sponges play a central role in reef environments, forming frameworks that bind sediments together and create habitats for other organisms. Both siliceous sponges with skeletons of silica and calcareous sponges with skeletons of calcium carbonate are common. They encrust reef surfaces, grow in branching forms, and provide stability to reef complexes. Bryozoans, colonial animals that filter feed with tiny tentacle-like structures, also contribute to reef frameworks and sediment production. Together with algae that precipitate carbonate, these groups build reefs that for much of the Permian stand as centers of marine biodiversity. The distribution of marine assemblages is strongly influenced by environmental conditions. In shallow, open shelves with good circulation, brachiopods, ammonoids, sponges and fusulinids thrive. But in restricted basins where oxygen is limited, communities are sparse and dominated by organisms tolerant of low oxygen conditions. Black shale intervals often show a sudden decline in fossil abundance and diversity, with only thin shells or small foraminifera present. These contrasts create a patchwork of environments, some highly productive and others nearly barren depending on the circulation and chemistry of local waters. Trace fossils add another dimension to our understanding of Permian seas. Burrows feeding trails and resting impressions preserved in sediments reveal the activities of worms, arthropods, and mollusks. In oxygenated zones, the seafloor is churned with bioturbation as animals dig and move through soft sediments. In anoxic zones, however, sediments remain laminated, showing no sign of disturbance. These differences provide clear visual evidence of where life flourished and where it struggled to survive. Reefs, as described earlier, begin the period strong but decline in the later Permian. Their fossil remains record successive waves of growth and collapse, reflecting sensitivity to environmental stress. In early Permian times, reefs extend along continental margins in great complexes supporting diverse assemblages of sponges, brachiopods, bryozoans, and fusellinids. But as conditions deteriorate, many reef systems vanish, replaced by layers of mud and black shale. The loss of reefs removes key habitats, reducing diversity further and leaving marine ecosystems more fragile. Predators in Permian seas are represented by nautiloids and ammonoids, as well as fish and early sharks. Cartilaginous fish ancestors of modern sharks and rays occupy top predator roles in some settings, with teeth and fin spines preserved in marine sediments. Their presence shows that despite environmental stress, food chains remain intact in many regions. Fish fossils also reveal adaptations to both open water and nearshore environments, with some species specialized for fast swimming and others for bottom feeding. Microbialites, structures formed by microbial communities such as cyanobacteria, become more prominent toward the end of the Permian as reefs decline. These microbial mats trap and bind sediments, forming stromatolite-like buildups in shallow waters. Their resurgence signals that more complex reef organisms are struggling, leaving room for microbial forms to dominate. This shift reflects broader ecological stress, as simpler ecosystems replace complex ones under environmental pressure. The chemical signals preserved in marine carbonates mirror these biological changes. Carbon isotope records show fluctuations that correspond to shifts in productivity and organic burial. Oxygen isotopes indicate warming trends and changes in evaporation. Trace element concentrations reflect variations in oxygenation and nutrient supply. These geochemical records, when combined with the fossil evidence, paint a consistent picture of seas that are increasingly stressed, with intervals of abundance interrupted by crises. Regional differences add complexity to the global story. In Gondwana, for example, marine assemblages often show a strong presence of Glossopteris pollen washed into sediments, linking land and sea ecosystems. In Tethyan basins, fusellinid-rich limestones dominate, while in Panthalassa, black shales mark the spread of anoxic waters. The variations demonstrate how local geography and circulation shape the distribution of life. Yet across all these regions, the general trend towards stress and decline is unmistakable by the late Permian. The final fate of many marine groups is extinction. Fusellinids, brachiopods, and sponge reefs all disappear or are reduced to remnants. Ammonoids, though they suffer heavy losses, survive in limited numbers and later radiate again. Bivalves more tolerant of stressed conditions begin to take on greater importance, setting the stage for their dominance in later eras. The shifting balance among these groups illustrates how crises reshape ecosystems, eliminating some lineages while opening opportunities for others. The seas of the Permian thus display both richness and vulnerability. They support diverse assemblages of organisms that leave behind thick limestone successions, yet they also record the growing reach of anoxia and euxenia. The fossil evidence shows communities of great abundance living side by side with basins of near lifelessness. This unevenness reflects the particular conditions of the Permian world, where geography and climate create sharp contrasts in habitability. The marine realm is both a showcase of evolutionary success and a warning of fragility, a balance that will eventually collapse under the weight of environmental change. The decline of coal swamps and the retreat of moisture-loving plants are among the clearest signals that the Permian world is fundamentally different from the Carboniferous before it. In the earlier age, vast equatorial regions are covered by dense forests of lycopsids, horsetails, and seed ferns that grow in waterlogged soils. Their constant accumulation of peat leads to the thick coal seams that define the Carboniferous. By the Permian, however, these conditions fade as climates dry, and the geography of Pangaea produces broad continental interiors far from reliable moisture. Coal formation does not disappear entirely, but it becomes rare and restricted to coastal or high-latitude regions, where rainfall or groundwater can sustain wetlands. The decline of coal swamps marks a turning point in both ecosystems and the global carbon cycle. Without widespread coal swamps, less organic matter is buried in sediments. This reduction in burial means that more carbon dioxide remains in the atmosphere, contributing to greenhouse warmth and further drying. In earlier times, coal forests acted as carbon sinks, drawing down atmospheric carbon dioxide and stabilizing climate. In the Permian, with their disappearance, this balancing process weakens. Geochemical records of carbon isotopes confirm this change, showing reduced rates of organic burial and a shift in atmospheric composition. The landscapes that replace coal swamps dominated by conifers, seed ferns, and open woodlands are less effective at trapping carbon in long-lasting deposits. The change in vegetation also reshapes ecosystems on land. Amphibians that once thrived in wet swamps now struggle as their habitats shrink. Fossil evidence shows a decline in many amphibian lineages replaced by reptiles and synapsids better suited to dry conditions. The soil record also reflects the change. Instead of waterlogged paleosols rich in organic matter, Permian soils often contain carbonate nodules, salt accumulations, and root traces of woody plants adapted to drought. These features indicate that soils are more exposed to air and evaporation consistent with reduced wetlands and coal formation. Fires become more important in shaping vegetation in the absence of dense swamps. Charcoal layers in Permian sediments show that fires are frequent, particularly in regions with seasonal climates. Drought leaves vegetation dry and flammable, and lightning from storms ignites widespread burns. Unlike swamp forests which resist fire due to constant wetness, conifer and seed fern woodlands are prone to ignition. This promotes the spread of fire-tolerant plants and reduces the dominance of species that cannot withstand regular burning. Fire thus acts as a selective force, driving ecosystems toward greater resilience to disturbance. In the southern continents of Gondwana, the decline of coal swamps is especially clear. Glossopteris forests dominate, spreading across vast areas, but even these are not the same as the swamp forests of the Carboniferous. Glossopteris trees are adapted to seasonality, with features that allow survival during dry or cold intervals. Their leaves show distinct growth patterns, and in some cases evidence suggests they were shed seasonally, much like deciduous trees today. This adaptation to alternating favourable and unfavourable seasons reflects the increasingly unstable climates of the Permian. Fossil leaf mats of Glossopteris in Gondwanan deposits show that entire forests could be shed and replaced in seasonal cycles. In Laurasia, the northern part of Pangaea conifers expand to fill niches once occupied by swamp vegetation. Their needle-like leaves, thick bark, and protective cones allow them to endure long dry seasons and recover after fire. They spread widely across uplands and drier lowlands, establishing forests that differ greatly from the swamp forests of the past. Palynological evidence shows an increasing dominance of conifer pollen in northern Permian sediments, confirming their ecological rise. These forests, though adapted to dryness, do not generate the same volume of peat and coal as earlier swamps, reinforcing the shift in carbon cycling. The decline of coal swamps also affects insect populations. Many giant insects of the Carboniferous, supported by oxygen-rich swamp environments, vanish as habitats change. Fossil evidence shows that Permian insects diversify into new forms, including beetles and early true bugs, which are better adapted to drier environments. Their association with conifer and seed fern forests suggests that new plant-insect relationships begin to develop, although pollination is still primarily wind-driven. The disappearance of swamp-adapted insects mirrors the broader collapse of coal swamp ecosystems. Marine systems feel the consequences as well. Reduced burial of organic carbon on land means more carbon dioxide remains available to circulate between the atmosphere and ocean. This contributes to higher greenhouse forcing and may influence ocean stratification and chemistry. The interconnectedness of land and sea systems becomes evident as the decline of one ecosystem contributes to stress in another. Geologists trace the decline of coal swamps through stratigraphy. In regions where Carboniferous coal seams are thick and abundant, the overlying Permian rocks consist mainly of sandstones, red beds, evaporites, and limestones. This sharp change in sedimentary faces is visible across continents. Radiometric dating and fossil evidence confirm that the transition occurs around the Carboniferous Permian boundary and continues through the Permian. The consistency of this pattern across Pangaea demonstrates that it is a global phenomenon, not a local change. The ecological consequences of losing coal swamps are long-lasting. Wetland-dependent species decline or vanish while drought-tolerant plants and animals rise. Carbon cycling shifts toward higher atmospheric concentrations, contributing to warmer and more variable climates. Fire regimes intensify, reshaping vegetation and landscapes. Soil systems evolve to reflect dryness and exposure. All these changes reinforce one another, creating feedbacks that lock ecosystems into new states. The coal forests, once so dominant, never returned to their former prominence after the Permian. From a reflective perspective, the decline of coal swamps illustrates how interconnected Earth systems are. The arrangement of continents drives climate toward aridity, which reshapes vegetation, which alters carbon cycling, which in turn feeds back into climate. Each part of the system influences the others. The geological and biological records together tell the same story, that a fundamental transformation takes place in the Permian, replacing one kind of biosphere with another. The coal forests give way to dry woodlands, swamps shrink to rare refuges, and ecosystems reorganize around survival in a harsher world. The legacy of this transformation is visible in the rocks we see today, where once thick seams of coal recorded endless accumulation of peat. Now red beds and sandstones speak of deserts and dry rivers. Where once fossils of giant lycopsids and tree ferns dominate, now conifers, seed ferns and drought-adapted vegetation take their place. The coal swamps are gone, and in their absence the Permian landscape is set on a course that will define the rest of the period. By the later stages of the Permian, signs of stress appear across both land and sea, recorded in fossil sediments and chemical markers that together reveal ecosystems under growing strain. The aridity of the continental interior continues, deserts expand and forests shrink. Rivers become more seasonal, and basins accumulate thicker sequences of red beds and evaporites. On land, many amphibian lineages decline sharply, surviving only in wetter refuges. Synapsids, though still dominant, show shifts in diversity, with some groups disappearing while others, such as dicynodonts and gorgonopsians, persist. The balance of ecosystems grows fragile as habitats become fragmented and specialized. In the oceans, reefs contract and eventually collapse. Earlier reef builders such as sponges and fusulinids vanish from many basins, replaced by microbial buildups that indicate stressed conditions. The widespread black shales of the late Permian point to expanding anoxia, with hydrogen sulfide appearing in chemical signatures. This means that large areas of the seafloor become uninhabitable, reducing the diversity of brachiopods, ammonoids, and other marine invertebrates. Groups that once flourished in abundance dwindle to sparse survivors. The loss of reefs removes structural habitats, compounding the decline by eliminating shelter and feeding grounds for many organisms. Geochemical records mirror these biological changes. Carbon isotope data from late Permian rocks show large and rapid shifts interpreted as evidence of disturbances in the global carbon cycle. Some intervals suggest pulses of carbon dioxide entering the atmosphere, and oceans overwhelming the ability of ecosystems to absorb or balance them. Oxygen isotope trends show warming in many regions consistent with greenhouse forcing. Trace metal enrichments in black shales, including molybdenum and uranium, confirm that anoxic and euxinic conditions expand through marine basins. These signals are consistent across continents, demonstrating that the changes are not local but global. On land, the fossil record reveals increasing turnover among plant communities. Glossopteris forests in Gondwana decline in abundance, with fossil leaf beds showing reduced diversity toward the end of the period. In northern regions, conifer forests remain, but they show evidence of stress from repeated fires and droughts. Charcoal fragments increase in late Permian sediments, suggesting that wildfires become more common and widespread. These disturbances alter soil profiles, leaving behind paleosols with carbonate nodules, salt crusts, and evidence of erosion. Vegetation becomes patchier, and ecosystems less stable. Animal life reflects these stresses. Large therapsids such as dinocephalians decline and vanish before the very end of the Permian, suggesting that environmental changes select against groups unable to adapt quickly. Dicynodonts, more versatile herbivores, persist longer and continue to dominate many assemblages, but even they show reduced diversity near the close of the period. Gorgonopsians remain top predators, but their distribution narrows. Smaller therapsids, reptiles and burrowers continue to survive, indicating that smaller body size and flexible habits may provide resilience in unstable environments. Fossil trackways from late Permian rocks show fewer large-bodied forms and more evidence of small diverse animals, a shift in the ecological structure. The sedimentary record captures signs of increasing instability. Many late Permian basins display repeated cycles of transgression and regression, with shallow seas flooding coastal areas only to retreat quickly. Each cycle leaves behind alternations of limestone shale and red beds, marking the instability of sea level and climate. Evaporate sequences in some basins become thicker, indicating intense evaporation, while black shales grow more frequent, showing repeated episodes of stagnation and anoxia. These rhythmic changes suggest that the Earth system is experiencing pulses of stress, not a single smooth trend. The fossil record of insects also reflects disruption. While beetles and true bugs continue to diversify, many older lineages disappear. Wing impressions and other remains from late Permian deposits show that insect faunas are in transition, with losses among groups tied to swampy habitats and gains among forms adapted to drier environments. This mirrors the changes seen in plants and vertebrates, with species specialized for moisture declining, while those tolerant of dryness survive. The reshaping of insect communities affects pollination and decomposition, further altering terrestrial ecosystems. Marine ecosystems are particularly hard hit in the later Permian. Brachiopods, once the dominant shelled animals of the Paleozoic seas, suffer major declines. Only a few lineages manage to survive into the Triassic. Bivalves, in contrast, begin to increase in number, a sign that they may have had greater tolerance for stressed conditions such as variable salinity or low oxygen. Ammonoids also decline sharply, with many families vanishing, though a few survive as the ancestors of later radiations. Fusulinids, which once filled carbonate platforms, go extinct entirely before the close of the period. The sharp reduction of these groups in late Permian layers shows that the marine biosphere is already in crisis before the final extinction pulse. The causes of these growing stresses are debated, but many lines of evidence point toward volcanic activity, particularly in Siberia, where the immense lava flows of the Siberian traps erupt near the very end of the Permian. Even before this peak activity, smaller volcanic events elsewhere may have contributed gases and aerosols to the atmosphere. These inputs alter climate-ocean chemistry and atmospheric composition. Mercury anomalies in late Permian sediments suggest volcanic emissions, and the timing aligns with many of the disruptions in ecosystems. While volcanism is not the sole driver, it appears to play a central role in the cascading stresses that unfold. One unresolved question is how quickly these changes occur. Some records suggest that ecosystems decline gradually over millions of years, with waves of extinction spread through the late Permian. Others indicate sharper pulses where diversity drops suddenly in short intervals. The answer may be that both patterns are present, with long-term background stress punctuated by rapid crises. Fossil sequences in South Africa, China, and Russia show evidence for multiple extinction phases, each reducing diversity further until only a fraction remains. The final catastrophe at the end of the Permian then completes the collapse. For paleontologists, the late Permian represents a critical window into how Earth systems can unravel when multiple stresses combine. Deserts, wildfires, and shrinking forests on land, coupled with expanding anoxia and collapsing reefs in the sea, show that ecosystems are interconnected. The fall of one group of organisms cascades into others, producing widespread instability. While some groups persist, the overall trajectory is downward, setting the stage for the most severe mass extinction in Earth's history. The rocks of the late Permian, with their black shales, evaporites, red beds, charcoal layers, and reduced fossil diversity, are silent witnesses to this global crisis. They show that by the time the final extinction pulse arrives, Earth is already under strain, ecosystems already weakened, and the balance between life and environment already precarious. The stresses of the late Permian do not come from a single cause, but from the combined weight of geography, climate chemistry, and volcanism together, pressing the biosphere toward collapse. In the closing chapters of the Permian, one of the most profound geological events in Earth's history, takes place the eruption of the Siberian traps. This immense outpouring of magma covers vast areas of what is now Siberia in thick layers of basalt. The eruptions last for hundreds of thousands of years, releasing extraordinary volumes of lava and, even more importantly, gases into the atmosphere. Estimates suggest that the area covered by the Siberian traps lava flows originally spanned several million square kilometers, with layers in some places more than a kilometer thick. The scale of volcanism is unlike anything seen in human times, and its consequences reach across the entire planet. The gases released during these eruptions include carbon dioxide, sulfur dioxide, methane, and halogens. Carbon dioxide contributes to strong greenhouse warming, trapping heat in the atmosphere. Sulfur dioxide forms aerosols that can reflect sunlight, causing short-term cooling, but when combined with water, It also produces acid rain that damages ecosystems on land and in shallow seas. Methane possibly released not only directly, but also from destabilized methane hydrates in sediments adds to greenhouse forcing. Halogens may deplete ozone, increasing the exposure of surface life to harmful ultraviolet radiation. Each of these effects alone would stress ecosystems. Together they produce a cascade of crises. The geological record provides multiple lines of evidence for these volcanic impacts. Mercury concentrations spike in sediments deposited around the time of the eruptions consistent with volcanic emissions. Carbon isotope records show sharp negative excursions reflecting massive releases of carbon into the atmosphere and ocean. These isotopic shifts are global, appearing in rocks from South Africa to China to North America, confirming that the event is not regional, but planetary in scale. Layers of volcanic ash are also found in some sections, marking the direct fallout from eruptions. The environmental consequences unfold in both land and sea. On land, acid rain from sulfur emissions leaches nutrients from soils, kills plants, and acidifies lakes and rivers. Fossil leaves from the late Permian show evidence of damage consistent with acid exposure. Glossopteris forests in Gondwana collapse with leaf mats preserved in sediments abruptly disappearing. Conifer forests in Laurasia show reductions in diversity with many species vanishing. The loss of vegetation destabilizes soils, increasing erosion and sediment delivery to rivers and coastal seas. This sediment influx further stresses marine ecosystems already weakened by anoxia. In the oceans, the injection of carbon dioxide drives acidification, reducing the ability of organisms to build calcium carbonate skeletons. Reefs already in decline collapse entirely as sponges, bryozoans and fusulinids vanish. Black shales from this interval indicate that anoxia and euxinia spread widely, covering continental shelves as well as deep basins. Hydrogen sulfide released from euxinic waters may even have reached the surface in some regions, poisoning marine and coastal ecosystems. The collapse of carbonate sedimentation in many basins shows that the chemistry of seawater was fundamentally altered. Climate models of the Permian suggest swings between short cooling episodes caused by sulfate aerosols and longer-term warming driven by greenhouse gases. These fluctuations add to the stress on ecosystems, as species already pressured by anoxia, acidification, and habitat loss must also endure rapid climate shifts. Estimates of temperature rise during the peak greenhouse forcing suggest increases of several degrees Celsius enough to make equatorial regions extremely hot and reduce the habitable range for many organisms. On land, such heat combined with aridity would make survival difficult for both plants and animals. The scale of extinction recorded in the fossil record reflects these combined pressures. In marine settings, more than 90% of species disappear, including most brachiopods, fusulinids, ammonoid families, and all reef-building sponges. On land, many therapsid lineages vanish, including the gorgonopsians, while the cynodonts survive in reduced numbers. Insects which had previously diversified suffer their only known mass extinction, with entire orders disappearing. The breadth of losses across different groups and environments shows that the Permian crisis is not selective to one habitat, but affects the entire biosphere. One important question is the pace of these events. Some studies suggest that the main extinction pulse occurs within less than 100,000 years, geologically a very short time. Others propose multiple pulses spread over several million years. High-resolution dating of volcanic layers and fossil sequences increasingly points to a rapid collapse, though preceded and followed by longer intervals of stress. This pattern suggests that the Siberian Traps eruptions triggered sudden environmental shocks that ecosystems could not withstand. The causes of the extinction are complex, and while the Siberian trap's volcanism is widely accepted as the primary driver, feedbacks amplify its effects. Warming accelerates the release of methane from permafrost and marine hydrates, adding to greenhouse forcing. Vegetation loss increases dust and sediment delivery to seas, promoting eutrophication and anoxia. Ocean stratification intensifies under warmer conditions, expanding oxygen-depleted zones. Each feedback compounds the others, creating a spiral of environmental deterioration. The result is the most severe mass extinction in Earth's history, reshaping the biosphere in ways that will influence all future life. Evidence for ozone depletion comes from fossil pollen and spores that show deformities consistent with ultraviolet damage. Some spores display abnormal wall structures, suggesting that plants were exposed to higher levels of radiation. If volcanic halogens or hydrogen sulfide releases did weaken the ozone layer, this would have exposed land plants and animals to intense stress, adding another layer to the crisis. While not all scientists agree on the scale of this effect, it remains a plausible contributor to terrestrial extinctions. The end Permian event highlights the interconnectedness of Earth systems. Volcanism alters atmosphere and climate, which in turn reshape oceans and land ecosystems. Plants decline, soils erode, rivers carry sediment to seas, reefs collapse, anoxia spreads, and animals vanish. Each link in this chain reinforces the others. The combined force of these processes overwhelms life on a scale never seen before or since. The extinction is not only the loss of species but also the dismantling of entire ecosystems and the restructuring of global biogeochemical cycles. When geologists study these events, they rely on stratigraphic sections that preserve continuous records across the Permian-Triassic boundary. In places such as South China, South Africa, and Russia, sequences of limestone, shale, and volcanic ash preserve detailed evidence of environmental change. Radiometric dating of volcanic layers provides precise ages, while stable isotope studies track shifts in carbon and oxygen cycles. Together, these records allow scientists to reconstruct the tempo and mode of the crisis with increasing clarity. The consensus that emerges is that the Siberian trap's eruptions through their massive release of gases were the central trigger, amplified by cascading feedbacks in the Earth system. The legacy of the Siberian traps is immense. The eruptions transform landscapes, eliminate ecosystems, and reset the trajectory of evolution. Entire groups of organisms disappear, leaving ecological space for new groups to emerge in the Triassic. The extinction is both an end and a beginning, though the recovery lies beyond the scope of the Permian itself. What is certain is that the Siberian traps stand as a reminder of how geological events on a planetary scale can alter life in profound and lasting ways. The end of the Permian is defined by the most severe extinction known in the geological record, an event that wipes out the majority of marine and terrestrial species and transforms the structure of ecosystems forever. The rock record across many continents shows a consistent and abrupt reduction in fossil diversity. In marine environments, brachiopods that once covered seafloors in dense beds disappear almost entirely. Fusulinid foraminifera, which had filled carbonate platforms in such numbers that their shells formed entire limestone successions, vanish completely. Sponge-dominated reefs collapse, leaving no large reef systems until long after the Permian. Ammonoids, nautiloids, and many other shelled invertebrates decline drastically, with only a few lineages surviving into the Triassic. Trilobites, already reduced by earlier extinctions, disappear altogether at this boundary. The loss is not confined to shelled invertebrates. Echinoderms, such as crinoids and blastoids, suffer heavy casualties, and most groups of corals vanish. Black shales deposited at this time record eosinic waters, their laminations free of burrows marking a seafloor nearly devoid of life. On land, the picture is equally stark. Glossopterous forests of Gondwana collapse rapidly, with fossil evidence showing whole mats of leaves buried abruptly, suggesting sudden die-offs rather than gradual decline. Conifers and seed ferns in the northern continents also suffer, with many species lost and ecosystems simplified. Insects, which had previously diversified into many new forms, experienced the only mass extinction in their history, with several entire orders vanishing. Among vertebrates, many large therapsids disappear. Gorgonopsians, the saber-toothed predators of the late Permian, vanish completely. Dinocephalians had already disappeared earlier, and now other groups follow. Dicynodonts survive, but with much reduced diversity, while smaller and more adaptable therapsids persist in scattered refuges. Reptilian groups also face losses, though some of the archosauromorph relatives survive, providing the lineages that will expand in the Triassic. Amphibians already in decline are reduced to a handful of survivors. The terrestrial biosphere becomes far simpler, dominated by fewer and more generalized species. The drivers of this crisis are multiple, but interconnected. The Siberian Traps eruptions inject immense volumes of greenhouse gases, driving rapid warming that makes equatorial regions intolerably hot for many organisms. Climate models suggest that global average temperatures rise by several degrees, while equatorial land regions experience extremes far above survivable thresholds for large-bodied animals. Ocean warming intensifies stratification, preventing oxygen from mixing into deeper waters. Anoxia and euxinia spread from basins into continental shelves, killing off most marine communities. Acid rain from sulfur dioxide emissions destroys vegetation, leaches soils, and acidifies freshwater systems. Ozone depletion, perhaps caused by halogen emissions or hydrogen sulfide release, exposes organisms to harmful ultraviolet radiation. Each of these stresses compounds the others, creating conditions where survival becomes increasingly unlikely. The speed of the extinction remains a subject of study. High-resolution radiometric dating indicates that the main extinction pulse may have occurred over less than 60,000 years, an interval so brief in geological terms that ecosystems had little time to adjust. Some records suggest earlier pulses of decline followed by the final catastrophic collapse. This pattern implies that ecosystems were already weakened by long-term aridity fire and episodic ocean anoxia. So when the volcanic eruptions peaked, they delivered the final blow to a biosphere already stressed. Geochemical signals of the extinction boundary are sharp and global. Carbon isotope values drop steeply, reflecting massive releases of isotopically light carbon from volcanic emissions and possibly from destabilized methane hydrates. Oxygen isotope data show warming trends consistent with greenhouse forcing. Mercury anomalies peak at the same levels, confirming widespread volcanic activity. Sulfur isotopes record shifts linked to intense sulfate reduction in anoxic oceans. These markers appear in stratigraphic sections across Asia, Africa, Europe, and the Americas, demonstrating the global reach of the crisis. Sedimentary evidence also captures the abruptness of the extinction. Layers of limestone rich in fossils are suddenly overlain by black shales or barren sediments. In South China, sections that once held thriving reefs change within a few meters of rock to deposits nearly devoid of fossils. In South Africa's Karoo Basin, diverse therapsid faunas give way to impoverished assemblages dominated by a few hardy species. In Russia's Urals and Siberia, plant-rich deposits end abruptly, replaced by sediments with little organic material. The consistency of these signals across the globe underscores the synchronous nature of the extinction. The aftermath of the event is a world nearly stripped of complexity. Ecosystems become dominated by disaster taxa species that can survive in stressed conditions and reproduce quickly. In marine settings, small bivalves and simple microbial mats spread where diverse communities once thrived. On land, hardy therapsids and small reptiles persist in simplified food webs. Plants recolonize with opportunistic seed ferns and conifers, but forests are fragmented and thin. For millions of years after the extinction, recovery is slow, with ecosystems unable to return to pre-extinction diversity levels until long into the Triassic. Scientific debate continues on the relative importance of different mechanisms, but the consensus is clear that the extinction is the combined result of volcanic greenhouse-forcing ocean anoxia acid rain and possibly ozone depletion. No single factor alone can explain the breadth of the losses, but together they create conditions beyond the tolerance of most species. The Permian extinction thus stands as a stark example of Earth's vulnerability when multiple stresses converge. The lessons drawn from this event are rooted in evidence. Fossils, isotopes, and sediments all align to show a biosphere collapsing under global change. The scale of the losses affecting both marine and terrestrial life highlights the interconnectedness of Earth's systems. When oceans become toxic, reefs collapse, and carbon cycles shift, land ecosystems also falter. When vegetation disappears, soils erode, and dust enters the atmosphere, further altering climate and ocean chemistry. Each system feeds back into the others, amplifying disruption. The Permian Period, which began with the unification of Pangaea and the spread of vast deserts, ends with the most catastrophic biological collapse known. The world that follows is profoundly different, shaped by survivors that rebuild ecosystems in simpler forms. The great coal swamps, fusulinid seas, sponge reefs, and diverse therapsid faunas are gone. What remains is a planet in transition, bearing scars that will influence the course of life for tens of millions of years. The Permian extinction closes one chapter of Earth's history, with finality leaving only the geological record as testimony to a world undone by the combined forces of volcanism, climate, and chemistry.